Welcome back friends, a very good evening to all of you. Welcome in another video of our Taking It Together lecture series, where today we will going to revise all the linear representation of enzyme kinetics. So let's get started with the video without any further delay. So first we have to learn why we are doing this, because we have a hyperbolic curve already, right? Where we are taking V0 in the y-axis and substrate concentration in the x-axis, and we are getting something like this. Then why linear representation of this hyperbolic curve? So the idea is we cannot determine various type of important properties of enzyme kinetics with the help of this hyperbolic curve. For example, determining of Vmax will become very difficult with the help of this hyperbolic curve. And as the determination of Vmax become difficult, then obviously the determination of Km will also be difficult. That's why scientists have decided to represent the Michaelis-Menten equation in a linear form. Now remember one thing, to represent Michaelis-Menten equation in a linear form in the graph, we have to write the Michaelis-Menten equation in a form of y is equal to mx plus c, which is a equation for straight line. Okay, now remember, if the value of the m becomes positive, then the graph will look like this. Okay, and if somehow the value of m become negative, then the graph will be something like this. Okay, that is the thing you have to remember. Now let's talk about various type of linear representation of Michaelis-Menten equation. So first and the most common one, that is the Lineweaver-Buck plot. For Lineweaver-Buck plot, we have just taken the reciprocal of Michaelis-Menten equation, right? So here if we try to if we try to write the entire equation in the form of y equal to mx plus c, then here remember m, which is the slope of that particular graph, will consist of a constant value. Okay, and now remember, in the Michaelis-Menten equation, the terms that are actually present, among them Km, Vmax are actually constant values. Okay, so most of the cases remember the m will consist of either Km or Vmax, or both Km and Vmax. Okay, now to write the Lineweaver-Buck plot or the equation of Lineweaver-Buck plot in y equal to mx plus c form, first we have to find a value that consists of constant value as well as variable, so that we can consider that particular value as mx, right? So now, and this is not only applicable for Lineweaver-Buck plot, along with in case of Eadie Hoftsee and Hanse Woolf plot, in both the cases we will going to see the similar thing. So here let's see this particular value. So here Km by Vmax will be the constant value and 1 by S is the variable. So we will consider this as mx. And remember, the C will again a constant value, and here we are considering C as 1 by Vmax. And remember here another important thing, that this C will going to be the intercept of y-axis. Okay, and the value which will consist of only the variable, we will consider that particular value as y. Okay, so I hope you can now find out which will be y, which will be m, which will be x, which will be c. Now I have told you just that the y-intercept will be 1 by Vmax. Now the question is, what will be the x-intercept? So for finding x-intercept, what you have to do, you have to take the y as 0, and then with the help of mx plus c is equal to 0, you have to find out the value of x, that is minus c by m. Okay, now by putting the value of c and m, you can get the x-axis intercept, which is in case of Lineweaver-Buck plot is minus 1 by km. Okay, so now here we have plotted all the things that we have derived. So in y-axis we will have 1 by v0, and in x-axis we will have 1 by s. I have told you that the y-axis intercept will be the value of c. So you can see the y-axis intercept is the value of c, and the x-axis intercept will be the value of minus c by m. that is we have derived minus 1 by km. So this is this one, and the value of m will be the slope, right? So clear, Lineweaver-Burk plot? Very good. So now let's discuss the advantage of Lineweaver-Burk plot. So Lineweaver-Burk plot allow us to determine the value of important terms of enzyme kinetics Km and Vmax very easily. For example, if you want to find out the value of Km, you can just take 1 by V0 as 0, and then by solving this equation you can find out the value of Km, right? So that is the idea. Now, disadvantage. There are some significant disadvantages also. For example, suppose you have performed some small errors during the experiment, and we all know while doing experiment, error will be a very common thing, right? There will be some sort of error, obviously, right? But when you will going to take reciprocal of this, as you can see here, the error will be magnified. That's the major disadvantage of Lineweaver-Burk plot. Okay, so small error in the determination of V0 become magnified when reciprocals are taken. So that's the idea of our Lineweaver-Burk plot. And on the basis of that disadvantage, we have created another type of another type of linear representation of enzyme kinetics that we're going to see now. Okay, so let's start. So as a replacement, you can say we have used Hanse-Woolf plot. Okay, so where it is just a further extension of Lineweaver-Burk plot, we can say, because to derive the equation for Hanse-Woolf plot, we will going to start with the equation of Lineweaver-Burk plot. Okay, what we will going to do, we will just going to add the substrate concentration in both the side. Okay, that means we will going to multiply substrate concentration in both the side. Okay, now by arranging the equation, we can get the y equal to mx plus c form of Hanse-Woolf plot. So how you will do this? So let's see this one. This is totally a variable term, right? So we can consider this as y, no issue. Now it is actually consists of substrate concentration and 1 by Vmax. 1 by Vmax no doubt is a constant term, and it is a variable term. So we can consider this as mx, and this is totally a constant term, so this is c, right? So now as m here is again a positive value, so the graph will be something like this, and you have also the value of x-axis intercept and y-axis intercept. So by putting all of this, you will get something like this. Okay, so that is the Hanse-Woolf plot. So now let's move on the next type of plot, which is the last one, that is Eadie-Hoftsee plot. Here the thing is quite different. Here we will not going to start with either Lineweaver, either Hanse-Woolf plot. We will going to start with the Michaelis Menten equation. What we will going to do, we will by taking the reciprocal, we will going to add Vmax in both the side. Okay, now by arranging this, we will get something like this. Now we have to write this thing as y equal to mx plus c, right? So y means variable term. So here we will going to send v in this side. Okay, so we will get something like this. So now v is totally a variable, so we can consider v as y, right? This is totally a constant term, so we can consider this as c. Km here is a constant, so it will be m, and v by s will be x, right? So here you can see the value of m is in negative, so we can say here the graph will be something like this, right? And the rest of the things are actually same. So here I can hope that you can easily find out the y-axis and the x-axis, as well as slope, intercept and other things. So we will not going to talk about this. I have already mentioned you how to find out this. Okay, so now let's talk about a major disadvantage of Eadie-Hoftsee plot. So disadvantage is, as you can see, in both y-axis and x-axis, velocity is present, right? So any small error in velocity will going to be reflected both in the y-axis as well as x-axis. This is the major disadvantage of Eadie-Hoftsee plot. Okay, so that is the three linear representation of our Michaelis Menten equation of enzyme kinetics, right? So I hope this video will be helpful for you. Thank you.